Here we're going to learn how to write Lewis electron dot symbols. And we're going to start with just atoms and ions. But the big goal of all of this is to be able to predict the shape of molecules. And the reason why is because if you know the molecular shape of a molecule, you can predict a lot about its properties, both physical and chemical. So it's pretty cool that you can just use pen and paper and figure out the shape of something so microscopic. Let's start by talking about the different types of bonds. We have two types of chemical bonds. We have ionic and covalent bonds. Let's start with the ionic bonds. Give a chemical formula of any salt. Potassium chloride. Ionic bonds hold the atoms in the salt together in a crystalline form. What's an ionic bond? Well, we have potassium ions surrounded by chloride anions in that crystal, and it's those oppositely charged particles that are electrostatically holding it together. Give a chemical formula of any molecule. Remember the trick to identifying a molecule. Just do not include a metal. In this entire periodic table, all of this is metals. Just don't include that. So if you just combine nonmetals, you'll always have a molecule. So let's just combine carbon and oxygen, carbon monoxide. Covalent bonds are what hold the atoms in this molecule together. Just what's a covalent bond? A covalent bond is essentially a tug of war for electrons. Between these two elements, you have electrons. And the carbon and the oxygen nucleus are just tugging on those electrons. Nobody really knows whose electrons are whose. And there's a tug of war going on for those electrons between those two atoms. And that's essentially a covalent bond. And that's what holds the molecule together. Lewis electron dot, or Lewis symbols for atoms and ions. How do you write them? Pretty much just write the symbol and then surround it with the valence electrons. So for example, carbon. We look at the periodic table to see how many valence electrons carbon has. It has 4, Roman numeral 4. So we would put 4 dots around carbon. For the carbon cation, +1 charge, we remove one of those valence electrons. So you're just left with 3. Draw brackets around it to show that the whole thing has a +1 charge. And then carbon -4 anion, we have 4 extra electrons, a -4 charge. So you'd have your 4 valence electrons. You're going to have 8 total now because you have 4 extra. In brackets, then -4. Why does aluminum form the ion aluminum-3 while ions of gallium, indium, and tellurium only form +1 cations? Well, let's take a look at aluminum's noble gas core electron configuration. Compare that to those other ions. Aluminum, noble gas core of neon, (3s2), 3p1. Here's aluminum's valence electrons. There's 3 of them, and there should be. It's in group 3. So when this forms an ion, we lose those 3 electrons. And we form aluminum +3. And that's just going to have the electron configuration matching neon, isoelectronic with neon. So let's check out gallium. Gallium is here, noble gas core of argon. So then it would be 4s2, 3d10, 4p1. It loses this 1 electron, and then it's left with the pseudo-noble gas core. Same thing with indium and tellurium. They lose their single p electron, and they end up with the pseudo-noble gas core. So all of these end up with a +1 charge. So the reason is that pseudo-noble gas core. Why does tin and lead form +2 cations? Well, here's tin. Let's write its noble gas core electron configuration. You'd have krypton, and then 5s2, 4d10, 5p2. When tin forms an ion, and tin goes to tin +2, what 2 electrons does it lose? Right here. It loses these 2, and it's left with a pseudo-noble gas core. Same idea with lead. Lead loses its 2 electrons in the p, and left with a pseudo-noble gas core. So again, the reason why is pseudo-noble gas core. What ions would you predict for N, O, and F? So for nitrogen, oxygen, and fluorine, you remember the idea is that you want to be isoelectronic with a noble gas. So for nitrogen to be isoelectronic with neon, it needs to gain 1, 2, 3 electrons. So that'd be N-3. Oxygen needs to be isoelectronic with neon, gain 2 electrons, 1, 2. And fluorine would just gain 1 electron. How about for phosphorus, sulfur, and chlorine? The same argument. They want to be isoelectronic with argon. So phosphorus would become phosphide with a -3. Sulfur would become sulfide with a -2. And chlorine would become chloride with a -1 charge. Why do you think +2 is the most common charge for a transition metal ion? The reason why +2 is the most common charge is that all of these transition metals have these s orbitals available. So they'll lose those 2. So +2 is the most common charge for a transition metal ion. Write the noble gas core notation for each ion. Iron 3. Well, first let's just write the notation for iron. Iron is going to be argon 4s2 3d1 2 3 4 5 6. So what would iron 3 be? Well, we'll have argon, and remember D10 and D5 are super stable. So can we get one of those? You bet. Let's remove the 2 from the S and 1 from the D. And we are left with the electron configuration for iron 3. You can erase the 4s0 if you want, if it looks better. Indium with a +1 charge. Here's indium. Krypton is its noble gas core. So we'll have 5s2, 4d10, 5p1. To create the indium ion, the +1 charge, can we create a D10 or a D5? You bet. Just remove that 5p1. So you can write 5p0, or just don't write it at all. Write Lewis symbols for the following. Phosphide. Phosphorus has how many valence electrons around it? Phosphorus has 5. And we have 3 extra, so that means 8 total. 2, 4, 6, 8. And we need to draw brackets to represent the -3. How the -3 is distributed over the entire atom. Gallium ion. Gallium has 3 valence electrons. But we remove 1 to make it a +1, and we're left with our gallium ion. Again, brackets to show that the positive charge is distributed over the entire atom. Use Lewis symbols to represent the transfer of electrons between the following neutral atoms to form atomic ions with noble gas configurations. So they want these to be neutral atoms. And they want these to be ions. Okay? So bromine has 7 valence electrons. Calcium has 2 valence electrons. So bromine has 7. Okay. Remember, these ions are always isoelectronic with a noble gas. And bromine, we know, is going to form a -1 charge. Calcium is going to form a +2 charge. So what happens is that this electron in calcium will go to this bromine, and this electron will go to this bromine. So we'll end up with calcium with a +2 on it, and those bromines are going to have 8 electrons around them with a -1 charge. Try the same thing with potassium and iodine, see if you can get it to work. Each potassium has 1 valence electron. Iodine has 7. Remember the game, potassium wants to lose an electron, so it will be isoelectronic with argon. Iodine wants to gain an electron, so it will be isoelectronic with xenon. So let's transfer that electron to the iodide. We're left with potassium ion, no valence electrons, so no dots, and the iodine now has 8 valence electrons around it, -1 charge. For each of the following, write the noble gas core, electron configuration, and the Lewis symbol. Arsenic is right here. We'll have argon, 4s2, 3d10, 4p3. The arsenic ion, we have to lose 3 electrons. We'll lose these 3 right here. So we're left with just argon, 4s2, 3d10. For silver, its noble gas core is krypton, 5s2, 4d, how many? All the way up to 9, because cadmium would be 10. And remember, you're not done. If we can make D5 or D10, we always do that. So our best answer would be krypton, 5s1, 4d10. Promote one of those electrons. That makes writing the electron configuration of silver 1 that much easier, because it's really obvious which electron we're going to lose. Krypton, 4d10. Which has a larger radius, nitride or phosphide? They both have a -3 charge, so that anion component cancels out. Let's just check and see which element is larger. Phosphorus is below nitrogen, so phosphorus is a bigger atom. So P-3 is larger. Because phosphorus is larger than nitrogen. So writing electron dot formulas of atoms and ions really is no big deal. You pretty much just write the symbol and then surround it with a number of valence electrons.